Hello everyone. So today we're going to look at a crashing question involving costs, and specifically we're going to be looking at an exam question from the 2023 Northern Hemisphere paper where I have filled out and completed the answers for A, B and C already by using our forward and backward scanning process to determine the minimum completion time for the project, which is part A. So my forward and backward scanning confirms 24 would be the minimum completion time. Determining the latest start time for activity D, I can locate that up here in the top corner, which is the green number 8 would be the latest starting time, and which two activities have a float time of 2 days each. Examining all of these double boxes here, I can see activity C, the difference between the EST and the LST is 2, so the float time is 2, and also for activity J, the EST is 8, LST is 10, so the float time is 2. They are the two activities that have a float time of 2 days, so the answers here on the side, 24 for part A, part B 8, and then for part C we have C and J are the two activities. But our main focus today is going to be on the crashing component. So moving on with this question, we have the owner would like to reduce the completion time for the project. 5 activities A, B, H, F and K all involve installation of pumps. If the owner installs a new brand of pump, it is possible to reduce the completion time of these 5 activities by a maximum of 2 days each. The question in concern is, what is the maximum amount of time that can be saved by using the new pumps in days? So the best method or most efficient way we can work this out is to use something called the table method, which you can see over here on the right hand side. So the table method consists of 3 columns, and in the first column we need to identify every possible path going from the start to the finish, and we need to write them all down. So there are quite a few paths that go from the start to the finish in this network, so we're going to need to figure them out and write them down here in the empty boxes. Once we've done that, we will need to determine the completion time for each one of the paths that we can identify from start to finish. Once that's done, we'll then talk about the reductions column. So to start off with, we need to figure out or write down all of the paths we can see running from the starting vertex to the finishing vertex. So if we run along the top, we've got A, D, I, K and L, and another path we could go straight through the middle of the network, which would be B, F, H, K and L. Examining the graph again to look for more paths from start to finish, we could have B, E, G, H, K and L. That's 3 paths in total so far. Then we would have B, E, J, L is another way through that network. So B, E, J, L. And then we can start by going through activity C first. We can do C, G, H, K and L, and then finally right around the outside here along the bottom, C, J and L. So C, J and L. So there are 6 paths, 1, 2, 3, 4, 5, 6 paths in total running from the starting vertex to the finishing vertex. 6 different ways we could travel through that network from start to finish. Once that's complete, we now write the completion time of every single one of those paths. So we need to analyze those paths and add the edges as we move forward. So starting from the first path, ADIKL, that's 7 plus 8, that's 15, 16, 17, 21, 22, 23. So the completion time for that one is 23. The next path, BFHKL, so that's straight through the middle, which is 5 and 4 is 9, and 6 is 15, 19, 20, that's 21. And then we have BEGHKL, which is actually the longest way forward, so that's 24. That is the critical path. And we can make note of that. I'll highlight that one in green because that is our critical path. So continuing on, looking at our next path, which is BEJL. So BEJL, which is 5, 8, 20, that's 22 from start to finish. Then going CGHKL, which is 6, that's 10, 16, that's 22. And then finally our last path is 20. So they're the completion times of all of the 6 paths in this graph going from start to finish. So this is what the table method should include: all the possible paths from start to finish and the completion time of each of those paths. Now we consider our reductions. So reading the question again, we're allowed to reduce activities A, B, F, H, and K, and each of those can be reduced by a maximum of 2 days each. So the third column in the table method should include a list of the activities we are allowed to reduce and the maximum amount that each of them can be reduced by. So they can all be reduced by 2, so I've written a -2 next to each of the activities to indicate they can go down by 2 hours or reduced by 2 hours. So now what I want to do is look at all of the 6 paths that I've listed here and identify whether we can make any reductions according to this reduction column. So looking at the first path, I have ADIKL. Look at the reductions column here and identify the activities we are allowed to reduce. So A is allowed to be reduced, D is not one of them, I is not one of them, K is one of them, and L is not. So I can reduce 2 of the activities along this path. Each one can go down by 2 hours each. So that would be a reduction of 4 hours for this path. So the new completion time of this path would be 19. And I make a record of that in that third column, which is applying the reductions. Now repeat the process for path number 2 I've listed here, which is BFHKL. Compare that to the activities we've got in the reduction column. B is one I can reduce, F is one I can, H is, K is, L is not. So here I'm able to reduce 4 activities and up to a maximum of 2 hours each. So that would be an 8-hour reduction along that path if I was to do the maximum. And we assume we can do the maximum. So the original path was 21. I'm going to take away the 8 hours and then have 13 as the completion time of that particular path. Repeat the process for the next path. So we have BEGHKL. Identify the activities we can reduce. So B, yes. E is not listed. G is not listed. H is listed. K is listed and L is not. So this is 3 activities that can be reduced, and each one can be reduced by a max of 2. So we assume we will subtract the max. So that's 6. 24 takes 6, gives us 18 as the new completion time of that path. Then path number 4, B, E, J, L. I'm allowed to reduce B. E is not part of the list, J is not, and L is not. So I can reduce B by 2 hours. So that would be, the original time was 20, take away the 2, then I can have that path reduced down to 20. The 5th path I've identified, C, G, H, K, L. Again, C is not one of the activities I can reduce, nor is G. H, yes. K, yes. L, no. So I can reduce 2 activities, each of them by 2 hours. So its original time of 22, I can subtract 4 and have that as 18. And then finally my 6th path here, C, J, L. C is not an activity I can reduce, J is not, and L is not. So no reduction time can happen here, so that path will stay as 20. So now that I've done all my reductions, applied to every single possible path, I can now actually figure out how much time I can save. And I can answer question part D. So our original critical path was 24 hours, and the new critical path, so having a look at all of the new completion times after reductions have happened, the critical path would be the longest way forward. So out of all of these possible paths, the longest path is 20. And it happens twice. That means there's 2 critical paths. And they both have a completion time of 20 days. So what that tells me is I'm able to reduce my original critical path of 24 down to 20. So the time I can save and make sure all activities are completed is 20. I can reduce it down to 20. So the time saved was, original time was 24. I can get it down to 20 hours. Days. This problem is about days. So I can reduce and save a maximum of 4 days in this problem. Okay, so original completion time 24, which is the critical path, and the new critical path is 20. So the maximum days I can save is 4 days. And that would be the answer to part D. So that's how I can approach that question, by using something called the table method. It must have all the possible paths from start to finish, their completion times, and then what their completion times would be after we make the reductions that are given in the question. Okay, so that's how I would answer that question. 4 days is the answer. Now, as I scroll down, I have another part of the question, the final part, part E. This says the installation of the new brand of pump and the associated reduction in the completion time for the 5 activities A, B, F, H, and K will incur an additional cost. The table below shows the 5 activities that can have their completion times reduced by a maximum of 2 days and the associated daily cost in dollars. So these are the same 5 activities that we could have reduced here in part D, and still by 2 hours. However, the cost is, the daily cost is listed in the table. So A costs 400, B is 450, F is 200, H is 350, K is $300. The question is asking, what is the minimum amount of money that the owner will need to spend to save the maximum amount of time? So the maximum amount of time we figured out here is 4 days. And basically what we're asked to do is, how could I save those 4 days? What reductions would I need to do to save the 4 days? That's what this question is asking. What reductions should I actually do to save the 4 days? And then how much will it cost? Once I'm able to identify the reductions, I will need to find the cost using the table listed here. Now, one important thing is when we're answering questions like this is we still want the original critical path to be the critical path after the reductions. We don't want to change the critical path. The original critical path was BEGHKL, shown here in the table method where the 24 is. We still want that to be the critical path. Now, according to the reductions column, I know I can get the critical path down to 20, according to this, but I need to figure out how I can do that. And now I need to analyze the graph. I need to go back to the graph and analyze that to see how I can get that down to 20. That will tell me what reductions I need to do. Okay, so make note of this. There's 2 critical paths, C, J, and L. Okay, so I've got a blank diagram here. So C, J, and L, that's a new critical path, which is a length of 20. And there's also another one here, B, E, J, L, which is also 20. So I'll highlight that in another color, B, E, J, and L. Okay, B, E, J, L. And they are both 20, if we count that. Okay. Oh, we can get them down to 20, sorry, after the reductions. So, we need to keep in mind that I want BEGHKL to be my critical path. Okay, the original critical path. If I come back up here, just to highlight that for you, that is going like this. That's the original critical path. Okay, BEGHKL. So that's what I want that to still be my critical path. And I know from my reductions table I can get it down to 20. So that's the aim. How will I get that down to 20? Looking at these reductions here. Okay, they're the possible reductions, A, B, F, H, and K. Alright, I can only reduce those. I can't reduce any other activity. They're the only 5 I'm allowed to reduce. So I need to do some analysing. I know that original critical path here with the green highlight is 24. And I want to start getting that down to 20. I need to get that down to 20, basically, by completing some reductions. Okay, so it's going to just be a little bit messy here, but I really want this green one there to be the critical path. That's what I want to be the critical path. So I need to do some analysing. Okay, now from that, what we do notice is if I was to move forward through these 2 critical paths, okay, I will have a 5 here if I was to move forward, and coming through C, I can either get to that vertex in a 6 or a 5 plus a 3, which would be 8 would be the highest. Now, if both of these critical paths should be 20 according to this reduction table, then I need to look at how I can get them down to 20. So 20 should be the overall that I'm looking at the end, but they're currently not 20. So if you add C, J, and L together, you do get 20. But if you look at the purple path, I get 5 and 3 is 8. 8 and 12 is 20, and then plus the L is 22. So the purple path is not currently at a 20, it's at 22. But I can make a reduction so that I do end up with 20 at the end by reducing B by 2. B is one of the activities allowed, and if I take the full reduction of 2 hours, then B goes from a 5 down to a 3. How does that help? Let's analyze it. So notice traveling along the yellow line to get to this vertex would be 6. But when I do the pink, travel along the pink line, it was originally 8, 5 plus 3. And as we move forward, we should always take the highest number. So we will take the 8. However, we know if I take the 8 and move forward, I end up with 22 as an overall completion time, not 20. So by reducing B by 2, you'll notice both the purple line and the yellow line both get to that vertex after 6 days. 3 and 3, 6, or 6 along C. So by making that reduction, I'm now here at 6. Okay. Now, traveling from here, I then travel through J, which is 12, plus 6 is 18, plus L is 20. So that's one of the reductions I'm going to have to make. So now the yellow line and the pink line are now both 20, as confirmed by this table method. I can get those two paths down to 20, but I had to figure out how. How could I make both of those the critical path and have their completion time set to 20? So the way I could do that was to reduce B by 2 hours, and now both the purple line and the yellow are both the critical paths and at 20. So I'm going to record what reductions I'm actually making. So on the side here, we have reduce B by 2 days. That was one of the reductions that I have made. And I'll just bring these closer down here so we can keep track of them next to the graph. Okay, that was one of the things we can do. So that ensures this is happening, that these two paths are set to 20. Okay, and that's as low as we can get them. This method is showing we can't get them any lower than that. So now we need to concentrate on the original critical path. Okay, so we need to keep in mind we still want BEG HKL to be the critical path, and it's currently not. So we need to make some reductions so that this will happen. Okay, and the completion time should be 20. That's our aim, is to get that path BEG HKL down to 20. Okay, so we just need to look at what other reductions do I need to make to get that path down to 20. So let's analyze it from now. So if we travel along B, which is now 3, we assume we've reduced B by 2 hours. So if we go 3 plus 3 is 6, plus G would be 10, plus H would be 16, plus 4 would be 20, plus the final L of 2 days, that's 22. So the original critical path is sitting at 22, and we need to reduce that down to 20. So I need to look at how that's possible, and I can only reduce A, B, F, H, or K. They're the only ones I'm allowed to reduce. Keep that in mind. So, looking at that path, B we've already reduced. E is not an activity I can reduce. G is not. H and K are. H and K are activities that I could reduce. Okay. Now, having a look at the cost of those, It's cheaper to reduce K. And the idea is, what's the minimum amount of money? So we're better off reducing K rather than H because it's cheaper. So that's why I'm going to reduce K. All right. Looking at the original critical path here in green on the side, my possible reductions could be H or K because they're one of the 5 that I could reduce, but K is cheaper, so we take that option. So I'm going to cross out the 4 on the K, reduce it by its maximum, and see if that's going to get my critical path, original critical path, down to 20. Okay, so the original critical path, let's have a look, would be 3 for B, 3 for E, so that's 6. Coming up through G, that's 10. Through H, that's 16. Plus another 2, 17, 18, 19, 20. So that, by making the reduction, if we reduce K by 2 days, my original critical path becomes my new critical path, or remains the new critical path, set at 20. So I get a bit of a tick. Okay. However, I do need to just check some of the other numbers in the network as well. I need to make sure once I reduce some activities, I need to make sure that it is and remains the critical path, that I haven't actually got some other path sitting in the network that's the critical path. So I do need to check that. So what would I really need to check? I should really be checking the path along the top, because that involves the activity K. The pink or purple critical path doesn't involve K, so I don't need to look at it, nor does the yellow one. I don't need to examine that any further. But I do need to examine the path along the top because I crashed the K, just to make sure that critical path is 20 and not some higher number. Okay. So if I go along the top, I go 7 plus 8 is 15, plus 2, that's 17, plus the 2 for K, that's 19, plus 2 for L, that's 21. So my longest way forward is 21, and it's not the 20. So that technically would mean my original critical path is actually not the critical path anymore, nor is this yellow one or the purple one. Those 3 are set at 20, but this path exists along the top, which actually equals 21. And so we need to fix that problem. Okay, we need to fix that problem. So by reducing K by 2 days, it does 2 things. It does make sure we've got B, E, G, H, K, L down to 20, but it's not the critical path, unfortunately, because it's longer. Okay, so we note after we do that reduction, the path A, D, I, K, L is 21 days. And is now the CP, which is a problem. Okay, because the longest way forward is always the critical path. So along that path of A, D, I, K, L, can I make any reductions? K's already been reduced, H is not on that path, F is not, B is not, but A is. So I'm going to need to make a further reduction, and it has to be activity A. So because we were at 21 days, let's just try reducing it by 1 hour and see the effect of that. We may not need to take full advantage of crashing it by 2 hours. 1 hour might be sufficient. Again, we want the cheapest, so let's go 1 hour first. If I crash A and reduce it by 1 hour down to 6, if I look now across the top, I get 6 plus 8, which is 14, plus the 2 for I, which is 16, plus the 2 for K, which is 18, plus the 2 for L, which is 20. So that's perfect. So that path of 21 has now been reduced to 20, which now is also a critical path. However, I've still got my original path, BEG-HKL, as 20, so still remaining as the critical path. So once I reduce A by 1 day, that path along the top, so DIKL is now 20, and that was my aim. Okay, it's now 20, so there are lots of critical paths in this. However, I got it down to 20. All critical paths now are 20, which was my aim from this table. This table method was telling me I could get the critical path down to 20, and we just needed to figure out all the reductions possible so that I can get the critical path, or paths in this case, all down to 20. There are multiple critical paths, but they are now all down to 20. So, I'm finished. I still have my original critical path of BEG-HKL. That is still the critical path, and it's 20. And all the other critical paths in this are now all 20 as well. And I know I can't go any lower than that because of this table method here. So I am finished. So I now look at all the reductions that I actually made. I reduced B by 2 days. So the cost, B costs $450 per day. So this is the minimum cost, which is 450 plus 450, so 2 lots of those. I reduced K by 2 days, so the reduction for 1 day is 300, so that's 300 plus 300, 2 days worth. And then I reduced A by 1 day, and the cost of reducing A is 400. So adding all of those together will give me the total minimum cost of $1,900, and that is the answer to the problem. The minimum cost to save the maximum time, which is those 4 days, the minimum cost will be $1,900. Hopefully this has given you a bit more of an insight on how you can crash a network involving costs.